mixers that we have discussed so far are double balanced, which means that no local oscillator frequency or RF energy appears at the output except for the mixing products. Now, if you have an unbalanced mixer, then either the output will have coupled energy from the RF port or the local oscillator port, and they usually have lower conversion efficiency. So a balanced mixer has a higher conversion efficiency, while an unbalanced mixer has a lower conversion efficiency. And why is that? Because you're wasting the power. For example, if you're transmitting a DC term, it's unshifted and you're wasting the power. So unbalanced mixers usually have lower uh, conversion efficiency. So, for example, an unbalanced mixer that will allow a low energy to feed back into the antenna, and the radiation could cause interference to the other devices. So you're not only losing the your conversion efficiency, you're also causing interference. So they're not much they're not more popular as double balanced mixers are. So for example, here is an unbalanced mixer that allows both the local oscillator and the RF energy to feed through the output. So you see over here is once you have this RF at the primary coil, this gets mixed up with the local oscillator on the secondary side, and the mixed products, both RF and LO, RF and the local oscillator parts, they get rectified, and then whatever the positive sum is, you get that at the output, but at the expense of you have the mixed products, you have the mixing of RF and LO, and with that you have the RF and the local oscillator energies as well. So the local oscillator and RF voltages are added here by means of a transformer, and then there is sum is rectified. The voltage at the output, which is equal to the sum of the voltages when the sum is positive, uh, and it is equal to 0 when the sum is negative. So that's the rectified output. This mixer is totally unbalanced. So you are getting both the local oscillator and RF signals, and the output together with the sum and difference frequencies. Another unbalanced mixer could look like this, which uses a single pole double throw switch. So instead of having plus V in minus V in, you see this is 0 volts, and this is plus V in. So at the output, what you get is again a pulse train, but this is not pulsating between plus V in and minus V in. This is plus V in and 0. So plus V in and 0, and this trend continues. So you have plus V in, you have 0. So it's like you are multiplying the signal by a square wave that goes from plus 1 to 0 instead of plus 1 or minus 1. This is plus 1 and 0 rather than plus 1 and minus 1. So it's the analogy is that you are multiplying a square wave with having amplitude, the high is plus half and the lower is minus half, together with a bias term of half. So what you're doing is you're multiplying your V in by a bias term that is half, and plus a square local oscillator waveform that has 0 DC. This is the DC term. Okay. So what you expect is, I mean, V in is going to multiply by half. So you're going to transfer the DC power as well. You're going to transfer the DC power, and this is going to you're going to lose 1/4 of the RF power. You see, the square term, the multiplication of V in with the square oscillator will produce upshifted and downshifted bands as expected. As before, we have seen this. You have the V in and V in product with the oscillator VLO will produce the shift not only at the fundamental but also at the odd harmonics offsets as well. But then this bias term that we are going to have at the output together with this LO is half V in. So this allows 1/4 of the RF input power to get through unshifted in the frequency, so which we don't desire. So usually unbalanced mixers you can see as a has a lower conversion gain, or conversion loss is more, you can say. So you see what happened over here is you had a plus half, and this is um, plus half and minus half. So this is your square oscillator, and if you add a DC term, then this is going to be plus 1 and this is going to be 0. So this is actually what is going on over here. So if this is not minus V in, you are also transmitting, transmitting 1/4 of the RF input power to get through unshifted in the frequency. So that's an unbalanced mixer. Now, formally, if what the switching mixer loss is, also I've talked about this before as well. Now, assuming that the source see a match load, so you have a maximum power transfer conditions, assuming a match load when it delivers the maximum power, the load is matched with the source. You have a maximum power delivery. Then some of the power on the load, of course, some of the power is at the desired sum or at the difference frequency. You can have the lower sideband or the upper sideband, if you whichever you wish to select. Then the ratio of this desired power, to the power available from the source is known as the conversion gain, which we have already talked. Now, for a diode ring mixer, the ratio is less than unity. It's the loss, it's not the gain. Then, if you recall, for a diode ring mixer with a local oscillator, I mean, what we have seen before as well. For if you have a square wave, then this is the 10 hertz signal was shifted not only at the fundamental but at the odd harmonics as well. So what happened was that, for example, if you wish to select the sidebands around the fundamental, not at the harmonics, and you're going to filter out the harmonics, the conversion gain can be calculated as such. So, for example, over here, once you expand the square wave for your series, you see that the amplitude at the cross product of the fundamental local oscillator with the reference signal, the amplitude is half 4 pi half, either for the lower band or for the upper sideband. So the amplitude of the desired sum or the desired sum or the difference frequency component is half Vs 4 pi 1/2, and while the amplitude available from the source was actually half Vs. So you see the power is proportional to the V square of the power, square of the amplitude of the sidebands, that is 1/2 square, 4 pi square, half square divided by 1/2 square is what you have, is the conversion gain or the loss. So conversion gain, once again, for the sidebands, this is for the LSB or USB, whatever you are selecting. For example, if it's this lower sideband at omega L, at the fundamental frequency, then that's the power. You see over here, V square. This is the amplitude. This is the amplitude over here. Divided by what is the available power is. So this is the ratio is 40%, or in logarithm this is power. So this is tan logarithm of 0.4052, that is minus 3.92 dBs. Usually you have, in practice, the loss could be by the other sources as well, like loss in the diode and transformer. So typically you can have this, the value could be like -5 or something, due to the loss in transformer and diodes